So we stopped on this slide in the last section, and I just wanted to add some more insight into this equation right here. So again, originally the Mohr cycle was used in the graphical form illustrated here. You can plot it, plot your S1, S3, and your beta. This is 2 times beta, and you can graphically determine shear stress and effective normal stress. And later came up with mathematical expression to do that right away. So you don't need to create this plot before you can estimate your normal and shear stresses acting on the plane of the fracture. And if you think about this equation, this is half of sigma 1 minus sigma 3. What's sigma 1 minus sigma 3? It's going to be this diameter, right? So that's the diameter of the difference between sigma 1 and sigma 3. Is this diameter of this circle. Is the diameter of the Mohr cycle is what I meant to say. And when you do half of the diameter, what do you get? The radius. So this is the radius, right? And that will also be this, right? So this length is the radius. And now to go from the radius to the vertical component of the radius, which is what tau is, right? Then you multiply by sine 2 beta. So basically that's what this equation is doing. It's taking the radius and multiplying it by the sine of 2 beta so that you get the vertical component of the radius, which is slightly smaller than the radius, as long as beta is greater than about 45, right? Because when you multiply by 2, you get the full 90. Good. How about for the normal stress? Well, we're doing a lot more. First off, we get the midpoint of sigma 1 and sigma 3. So that's what this is, average of sigma 1 and sigma 3. So this is sigma 3, this is sigma 1. It's going to get to the midpoint, which will be right here. But what are we looking for? We're looking for this distance. So we need to subtract out some value here, all right? And that value is actually related to cosine of 2 beta, and that's what this is going to be. So if you calculate this value, you will see it's always going to be negative. And it basically moves the point from this point to sigma n. And that's how you get the normal, effective normal stress. And this gives you the shear stress on that plane of the fracture. So if you start out with sigma 3 being equal to 0, which corresponds to what type of test? Uniaxial test, right? Sigma 3 equals 0. Then you use the value of sigma 1 at the time the rock fails, right? What's that? It's called UCS. Sigma 1 at the time the rock fails is the unconfined compressive strength, because sigma 3 is 0, and that's this circle right here. Then you go to higher values of confining pressure, and you get a new, so this is a new value, right, of sigma 3 confining pressure, and you get a bigger circle, and you keep doing that. And how do you get the circle? Basically use a given value of confining pressure and perform the test until the rock fails, so you get the rock strength at that confining pressure, find the midpoint and draw a circle. So that's how we're coming up with these circles. And if you keep doing that at higher values of confining pressures, and you're getting higher values of rock strength, because rock strength increases as confining pressure increases, then you can try to connect a curve through the tangents through all these multiple circles, and that is your Mohr failure envelope, because you cannot exceed that stress value. Your rock will fail before you exceed them. So it basically gives you the maximum allowable stress state. Stress state cannot exceed it. You can get to it at which point the rock fails. And that's why it's the envelope that bounds the material failure. And again, this is shear stress versus effective normal stress. So instead of using a curve, which is what you actually will get when you perform the experiment, we like to simplify it and use a straight line because it's easier, right? You only need two parameters to define the equation of a straight line, but you will need several more parameters to define the equation for the curve. So that's what the Mohr Coulomb failure line is. It's just one straight line, and it's defined by two parameters, intercept and slope. So intercept is the cohesive strength or cohesion of the rock. So those two terms are used interchangeably. Cohesive strength or cohesion, that's the intercept of that failure line. And the slope is the coefficient of internal friction, mu sub I. Very important that you have the I there, because you will later see there's another mu that doesn't have the subscript I. And this is the coefficient of internal friction. So the slope and the intercept defines the equation of the line, right? Which is the equation of a straight line. Y equals, slope is this mx plus c or b. All right. And this is y, and this is your slope m. And the cohesive strength of the rock is related to UCS. It isn't the UCS. It refers to the force that holds the grains together, and it's different from UCS. So how do you get UCS? Well, again, we had illustrated UCS before. UCS is here. So from the intercept, you can draw the circle that will just touch that straight line. That's all from geometrical calculations in mathematics. And you know one point here, you can draw a circle that will just touch this, and that will give you your UCS. So given the slope, given this equation, which means you are given SO, you can mathematically find UCS. And that equation is right here. And you can see it's a function of the SO and the coefficient of internal friction. You can also find it geometrically, like I said, keep drawing circles starting from this that will touch this line and also touch the origin, and you will get UCS that way. So given SO and the slope of the line, you can mathematically obtain UCS. So failure envelope describes how the strength increases with confining pressure, right? Circles increase indicates S1 is increasing, and it indicates the rock strength is increasing, right? Because that's the maximum strength, the maximum stress the rock can withstand at that confining pressure. I should also mention this other point, which is at any S3 value, because you have this line, you can draw a circle, and that upper point of where the circle meets the horizontal line is the maximum stress the rock can handle. So given any S3, the Mohr circle tells you how large S1 can be. Very important to make that point. And here I'm just illustrating, if you had drawn a curve through it, you will have got the failure envelope, but we can approximate with a straight line like I explained previously. Here the slope is 0.9, and all of these are actual circles based on an experiment. And instead of working in this form where you're plotting shear stress against effective normal stress, we actually in practice work with S1 against S3. And the slope will no longer be mu I, right? It's a different plot. It's not tau against effective normal stress. It's S1 against S3. So the slope is actually called N. And from N, you can get mu I mathematically using this expression. And the intercept of this line directly gives you UCS. So the intercept of this line is UCS, CO, and not SO, which is the intercept of this line. That's the important point to note here. Another point is that coefficient of internal friction is not as important as the cohesive strength. A higher value of the cohesive strength, which directly gives you UCS from the equation I showed previously, is what indicates that the rock is strong. So high values of UCS, higher strength of the rock. But mu I being higher doesn't necessarily mean the rock is stronger than a rock with a lower mu I value. And when you're working in this form where you plot S1 against S3, which is what we work with more, we have a slightly different version of the Mohr equation. So it's S1 as a function of S3, right? And the slope is Q or N. And the intercept is CO, which is UCS. Slightly different from the version I showed before. And we can write Q in this form, which is the slope of the equation, or N, and that's it right here. And that's how we're able to find mu I from the slope of this form of the equation. It's just another way of writing the same Mohr equation, and you will see tau being written in this form instead of what you had on the previous slide.